Hello everyone. So today we have Prof. Tonry from the Institute for Astronomy and the University for Hawaii as our speaker. He's based in the USA, so thank you very much for staying up late or waking up very early to be able to make this. He will be talking about ATLAS and over to you. Thanks.
Okay, good. So let me share my screen. Share screen. Here we go. Share screen. And everybody see the screen now? Atlas Hawaii?
Yes, we do.
Okay, good. So what I'd like to do is describe ATLAS to you. As I'm sure you know, we have a ATLAS unit coming to Sutherland very soon. We've been working on it for 2 years. Larry and I visited South Africa 2 years ago and picked a site and met with Amanda and Nick, and we're almost ready to go. And we're very excited about this because instead of having these 2 lousy telescopes in Hawaii, we will have 4 telescopes, 1 in Sutherland, 1 in Chile, and 2 in Hawaii, and we'll have all sky coverage. So we're really looking forward to that. At this moment right now, we have concrete in Sutherland, we have a dome on its way, the mountain telescope are done, and we're waiting on a Schmidt corrector and a camera, which have been CCD, which have been slowed down a little bit by COVID-19, but we're getting there. So what I want to do is describe to you a little bit what ATLAS is, a little bit about what ATLAS does, and then I hope to give you some sense of what ATLAS could mean to you and why this should be interesting to you. So anyway, why should we survey the sky? ATLAS is a sky survey system, and one answer is just because we can. Technology has really opened up in the past 10 years or so, and you know, the concept of basically imaging the whole sky every night it's not a problem now. 10 years ago, very hard, not a problem now. And there's all sorts of things in the sky that change, as you know, and so therefore you don't necessarily see the same sky every night, and it's worth looking over and over and over again. Another reason is just sort of unknown unknowns, who knows, you know, interesting, weird discoveries. Third possibility is known unknowns. There are lots of strange and exotic things, and if you survey large volumes in space and time, you can find them and start seeing some patterns and start making some sense of what they are. And then of course there's the known knowns, just lots and lots of useful things. Like if you want to find a ton of auroral Lyrae for mapping out galactic structure, or you want to find a ton of supernovae for mapping out cosmological structure, this is how you find them. So in a nutshell, what ATLAS is it's a small Schmidt telescope. It's a 1/2 meter aperture, sits inside of an ash dome. It's on a German equatorial mount. It has a 10K camera, so it's 110 megapixels. It collects a lot of data, so about 1,000 images a night times 100 megapixels a piece is about 100 billion pixels a night. And so we pull that out with Ethernet that's, we need about 50 megabits per second in order to keep up with the data flow. And so basically we can, you know, one of these telescopes can observe the whole sky once per night. And soon, when we have 4 of them, we will be able to observe the entire sky, except for a cone around the sun, 4 times per night. The sensitivity of this thing is very carefully determined to be just about 20th magnitude per exposure, about 19.5 or something like that. And it turns out, as you'll see, this is critical for the ATLAS mission and why we're funded. And so it is a little bit less deep than other sky surveys, such as Pan-STARRS and ZTF. It's considerably less deep than LSST, but it's a lot deeper than other sky surveys like Assassin, for example. So anyway, there's a lot of computers, there's a lot of software. Basically, we turned on in the middle of 2015, And we operated for about 2 years with a substandard Schmidt corrector, so our images were a little bit fuzzy, which is very annoying. And then we got the Schmidt correctors corrected in the middle of 2017, and we've been taking much sharper images ever since from our 2 sites. And this kind of illustrates exactly what we're doing. So we use difference imaging to find things that change. This picture of the Lagoon Nebula, we don't care about the galactic plane, we just go over everything. We observe the celestial North Pole, we look at Polaris all the time, we go right through the galactic plane. And the little green circles here on the right are showing you asteroids, and most of them you can actually see them moving. The red circles are showing you where variable stars are bright, and black circles, which are kind of hard to see, are showing you variable stars that are dark. And in fact, if you can see the cursor right up here in the middle of the center of the top, there's a variable star that's actually blinking black, white, black, white, black, white on the duration of our exposure time. So to date, we've taken about 2 million images. With 4 telescopes, we'll be taking about 1 terabyte per night of raw data, and that condenses to, or that expands to about 4 terabytes. So it's a lot of stuff. Obviously, we don't have an army of students who are reducing this stuff. It's a fully robotic system. So, for example, if the internet connection goes away, the system doesn't care. It keeps on taking data all night long. Opening and closing the dome is required. And when the internet comes back, we can pull the data down and start looking at it. If you want, you can actually watch us in operation. If you go to fallingstar.com, that's our website, and if you look around a little bit, you can see a thing that says dashboard. Currently, you can only go and visit Mauna Loa and Haleakala because those are the only 2 that are operational as yet. But soon, you'll be able to go to the Sutherland site or the Chile site and watch them operating. And in fact, if you tack a /weather/ on the end, you can actually see the weather station that we've put on Sutherland in operation right now. And so we can watch this all night long. It's really kind of fun because over here on the left, you can watch the lights going green and red and so forth and so on as things happen. This shows kind of the view of the sky. You get a nice graphic here that shows where the telescope is pointing, what are the images that it's taken, and so forth and so on. I find this eternally amusing to just sort of watch. And so what we've got is a dome, and right now there's concrete at Sutherland. Soon it will be a dome, and then inside the dome we put a mount, German equatorial mount. This is what Haleakala looks like, this is what Mauna Loa looks like. And then on top of the mount, we put the Schmidt telescope and a camera and so forth and so on. I mentioned all this before. An interesting thing to understand is our filters. We use primarily 2 different filters. One we call cyan, and as you can see, cyan is essentially G+R. And we use that when the moon is down. When the moon is up, we use what we call our orange filter, which is almost exactly R+I. And so these filters overlap. They're a little bit broader than the standard Sloan gun filter because it gives us a little bit more sensitivity. But at the same time, alternating between filters means that we get interesting and useful color information on objects. So the main telescope and camera saturates around 11th magnitude. And if you want to go brighter than that, you can't do photometry very well. The stars are going to be saturated and bleeding. On the other hand, what we do is we piggyback a 35 millimeter camera on the telescopes, and we take synchronous pictures with these things. And we fully reduce and calibrate these things so that we actually have can extend our photometry down to about 6th magnitude by using these things. The photometry isn't quite as good because it's RGB Bayer pixels and so forth, but nevertheless, you can learn a lot about bright stars using these things, or bright transients. And wait, don't answer yet, because in addition, we have this, this weather station that I mentioned, except that the primary instrument here is a fisheye, is a 35mm camera, again, with a fisheye lens. And once again, we treat it as a real, honest-to-God astronomical instrument. We calibrate the thing. In a typical fisheye image, we find thousands of stars, and we can do photometry to better than the 10th of a magnitude for sure. For example, it's really easy to see Polaris varying in the fisheye data. So this simultaneously gives us photometry down to about 0th magnitude. And also it tells us about the sky clarity and whether there are clouds present. So we use this. I mean, for example, here's the box at Sutherland. Here's snow at Sutherland. We never see, no, that's not true. We see snow in Hawaii as well, but this was surprising to us. But you know, here's an image of the sky taken with the fisheye camera, and obviously there are clouds present that you can notice because they're lit up by the sodium lights from Honolulu. But you know, how do you quantify this? Where should you be observing? And right here, this tells you. Here's all our stars photometered by the fisheye thing, and you can see there are some patches that are really quite transparent, and other patches that are quite opaque. And so we can take advantage of that. There's a ton of software, robotic robotic software to operate the telescope, robotic software to reduce the images and produce these difference images. I'm not going to go through all these dumb colorful boxes, but just to say that there's a lot of software here. It is all autonomous, it is all robotic, so that you know, things basically automatically reduce as the images are taken. And in fact, from shutter close to final results of difference photometry and everything takes about 30 minutes or so. This could probably be faster if anybody cared, but we don't really care. For our main mission, which is finding asteroids, we have to basically see the asteroid 4 times in order to really see its little track across the sky. And we need to spend some time waiting for it to move along this track. Typically, it's about an hour or so. And so as long as this latency of data reduction is significantly shorter than the amount of time we have to wait for the asteroid motion, we're okay. So anyway, that's in a nutshell, that's what ATLAS is all about. That's what we're building at Sutherland. There's a lot of byproducts that are coming out of ATLAS. I think I mentioned that this is funded by NASA to find dangerous asteroids. And I'll talk in a minute about, you know, what we're doing to find dangerous asteroids and whether we're really satisfying NASA and so forth. But in order to carry out this asteroid mission, we're trying to be as useful as possible for other things. So there are all these technical byproducts, such as software that's actually portable and useful for other people that we're trying to provide. And we've made an all-sky photometric catalog of GRI, actually GRIZ, but GRI primarily. And so it's basically all stars to essentially 19th or 20th magnitude, merging together Gaia DR2 astrometry with a whole bunch of different sources of GRI photometry that we think is basically the best in the world. We hope with Gaia DR3 that they will actually be able to do better, maybe, than we did, but it remains to be seen. Anyway, you can get that from Space Telescope if you want. And the thing that's kind of interesting about ATLAS is it's, you know, we have a very good time sampling, better than other surveys. So, you know, LSST is going to essentially look at a spot on the sky once every couple of days, and maybe with 1 exposure, maybe with 2 exposures immediately next to one another. So if you wanted to use LSST data for example, get a period of an aurora Lyrae star, really bad time sampling. Whereas what ATLAS does for its asteroid mission is to take these 4 exposures spread over about an hour or so. And when you consider that you got 4 exposures now, and then 4 exposures a day later, and then 4 exposures a day later with sort of random phasing, it actually fills in very well for uh, uh, getting the time history of variable things. And as I mentioned, we deliberately are in an interesting magnitude regime of approximately 20th magnitude per exposure. So it's not incredibly deep, but at the same time, it's deep enough. So how about our NASA mission? There was this asteroid that was supposed to pass really close to the Earth in 2013. This is 2 years before we turned on, but you know, everybody was looking for it. It was going to come really close. And on that very same day, this other asteroid came out of the sun and hit the Earth over Chelyabinsk and blew up with this big explosion. And it was borderline serious. A number of people were injured. There was some damage and so forth and so on. If it had actually been closer to the city of Chelyabinsk, actually people would have died. Or if it had been a little bit bigger, people would have died. And this is exactly the sort of thing that ATLAS is supposed to be looking for. And obviously, we're not going to prevent it. But if we can discover this asteroid a couple days before it hits, we can tell people about it. And there can be news reports that say, when you see a flash, don't go next to the window and peer outside to see whether what caused the flash. Stand back from the window because there's a shock wave that's going to come along in a few minutes. So we've done some simulations of what our probability is of finding asteroids as a function of size. And on this graph here, I show in green points what we were able to achieve with just 2 telescopes in Hawaii. The 4 telescopes that are coming along, one in South Africa, one in Chile, will essentially double our ability to find dangerous asteroids. Chelyabinsk was a half a megaton. It blew up 30 kilometers in the sky. It was borderline pretty dangerous. If you go a little bit larger to an explosion that's 5 megatons or 10 megatons or something like that, then you get into kind of a Tunguska range, and then it's definitely serious. If it blows up over the ocean, it's okay. But if it blows up over land, over some populated area, it's really bad. And so our ability to discover Chelyabinsk is going to be, you know, 40% or so. Our ability to discover Tunguska is maybe 60%. And the reason it's not 100% is, well, sometimes they come directly out of the sun, the way the one at Chelyabinsk did. Sometimes you just happen to be under bad weather at the sites that you've got, and you're not able to observe it. But this is what we're doing. This is our mission. This is what NASA pays us to do. And we're getting pretty good at it. Here's an example of our discovery page that humans look at to decide whether we have a real asteroid or not. Right here is a set of thumbnails on the left that show a piece of image where we think there's an asteroid. The middle set shows the difference images, and the stars have been mostly erased, and leaving behind this little blip. It's not in the same position relative to the stars. It's moving, so we fit a trajectory to it and decide, oh, that really looks like an asteroid. And here it is, kind of confirmed with red crosses and so forth. But the thing that was particularly interesting about this one is down here, the distance from the Earth when we discovered it that we can get from 4 observations was only 2 lunar distances. And also its radial velocity was 3.6 kilometers per second headed out. which means this thing came really close to the Earth, and we caught it on its way out. And in fact, we got a very high resolution photograph of this thing. This was the Tesla Roadster. And we saw it headed out. And it gives you a sense of what the ATLAS sensitivity is all about. Something the size of an automobile that is 2 times as far away as the moon is really obvious to ATLAS. And that's where the 20th magnitude comes from. It's basically time to hit the Earth and size of impactor and therefore consequence of whether it matters that it hits the Earth. In 2018, actually, we did help discover an asteroid that hit the Earth over South Africa. So it was 2018 LA. It was discovered by Catalina Sky Survey, actually. And ATLAS is west of Catalina, so we came along later and were able to supply some points that told people where to look for the impact. One thing that we're kind of gleeful about is with a site in South Africa, we're going to be east of Catalina, which means we're going to be seeing it first. And all these discoveries that Catalina gets, we will grab away from them because we're east of them. There's other things that we can do. So that's all astrometry. Photometry, we can find lots of interesting things. This is a case of an asteroid that suddenly grew a tail. And it turns out that it's rotating fast and is probably breaking up. It's just sort of spontaneously breaking up. We discovered it and told people, look, if it hadn't been flagged, nobody would have noticed. So moving on to a photometry of asteroids, this is what a light curve of an asteroid looks like as a function of time. As you can see, it's a complete mess. It goes up, it goes down, it ranges from 16.5 to 19th magnitude. Most of that is just because it's orbiting around the sun, and so therefore the illumination direction and the distance is changing. So if you take those 2 factors out, you see this, and it's still extremely noisy. So you might think that the ATLAS photometry is really terrible and these error bars are underestimated. But no, in fact, what's happening is the asteroid is rotating. And you can actually fit a period to this, and if you do, you end up with a light curve that looks like this. And once you have this light curve, it's very interesting because you get the period, how fast is it rotating, but also you can put together photometric points from the 2 different filters, and you can get a very accurate color for this asteroid, which tells you something about composition and families and where did it come from and so forth. So Nick Erasmus has been taking advantage of this to look at various things, one of which is the Flora family, where he thinks that he sees kind of an interloper collision that happened in the Flora family long ago. So here's some pictures from his from the papers that he's working on. And in principle, we can provide information like this for 100,000 asteroids. But all of this stuff that we do for asteroids, this is what we're paid to do, but all this stuff that we do for asteroids has essentially all the other variable sky available. So here's a picture of M107 that we took, some random night with some random exposure. And this is what our difference image looks like. So you can clearly see where the Aurora Lyrae are. Some of them are positive, some of them are negative. And it's not as though we, had a campaign that night to go observe M107. We observed the whole sky. So all the globular clusters that are not behind the sun, we do the same darn thing every night. And we look at these things 4 times over the course of an hour. So it's very easy to put together an Aurora Lyrae light curve, for example, get a period, get photometry, and so forth and so on. We call this our variable variable star catalog DR1, and it's okay, but it really needs to be done again and again and again and again. We've moved far beyond the number of observations that went into this thing. On the right, you can see what a variable star looks like, an eclipsing binary, for example, at 13th magnitude in ATLAS data. and at 18th magnitude in ATLAS data. So at 18th magnitude, there's like tons of signal to noise, no problems fitting a light curve, light curve to it and determining a period and so forth. At 19th magnitude, it gets a little bit harder. Once you do this, you can start doing all sorts of interesting statistics on variable stars. So this is a paper that Ari Heinz put out that where we found millions of variables. You can, on the left, you can do statistics of various types of variables that we see, looking at period versus amplitude and so forth. There's a bunch of weird light curves that he found. This one on the upper right here, to me, is the most interesting. This is one where the light curve only has an amplitude of about 1/100th of a magnitude. It's periodic, so a Lohm-Scargill periodogram will pick it out very easily, but nevertheless, it's only barely variable, and I think it's pretty cool that we can find that. Anyway, this is all available at Space Telescope, but I need to stress that it's way out of date. We have so much more data, so much better data since then, and also this data release 1, for various reasons, only spans declination -30 to declination +60, more or less. And now we're pretty complete from -45 to North Pole. And as soon as Sutherland and Chile get going, then we all start. There's all sorts of other sciencey things. I was really shocked to discover that we can actually see the incoherent pulsation of giant stars and get the primary pulsation period, which is related to the luminosity, temperature, and mass. It's just the brightest stars, but nevertheless, you can do astroseismology on 60,000 stars in the Milky Way from ATLAS data. And all comes for free because we're observing all these stars all the time, every night. So moving out of the Milky Way, there's cosmic variables and transients. So specifically supernovae, we see tons and tons and tons of supernovae. As of today, I guess, we've discovered about 6,500 supernovae. It's not a question now of surveying galaxies to look for supernovae or things like that. We're observing all the sky all the time. So essentially we see all the supernovae except the ones that are behind the sun that are bright enough. Type 1a supernovae, in principle, we can see about 5,000 a year, and we certainly will see the bright ones. We also look at essentially all AGN, QSOs and AGN all the time, and just build up these ridiculous light curves that wander all over the place, and you can flag particular ones that you're interested in to find out whether it's suddenly buried. You can look at them for to look for events that would be useful for reverberation mapping, any number of interesting projects that you can do with AGN. And the thing to remember is we take 4 exposures per night, and although one exposure is 19.5 magnitude, if you average the 4 of them, then the limiting detection is more like 20.2, and if you average a week's worth, it's more like 21, and if you average a month's worth, it's more like 21.5. So if things are varying slowly enough, you can actually build up extra sensitivity. I'm particularly personally interested in supernovae, type 1a supernovae, as distance signposts. And this, for example, is a ATLAS data in the orange and the blue colors for just a random type 1a supernova at a redshift of 0.044 that we're using in a project to find to measure peculiar velocities. And so you know, this picture down here in the left shows a Brent Tully view of what the world looks like. And we're this tiny little red dot in the middle. And he says, oh, never mind this great attractor and coma stuff. No, 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 no. There's a Shapley attractor and there's a dipole repeller up here. And it's creating a huge, huge flow from this direction to that direction. And so therefore, the predictions for the Milky Way velocity with respect to the CMB is totally sensible because it's, you know, this gigundous flow is taking place. But we can test this with supernovae. You know, we don't have to necessarily use galaxies as distance indicators. So anyway, we're working on a project with this with a grad student named Aaron Doe, and slowly collecting data. Quasars. So we looked at the milliquas sample, for example, and this ATLAS DR1 that I mentioned. We've got light curves for 100,000 AGN brighter than 18, and about a third of them are clearly variable. This ATLAS DR2 declination minus 45 doesn't exactly exist yet, but one of these days it will when somebody gets motivated to do it. And it'll sort of double the number, the signal noise will improve, it'll be better time sampling, better duration, and so forth. And here's a bunch of examples, light curves of AGN. The sort of brown and dark blue things that aren't varying are some reference stars nearby, so they shouldn't be varying. And then the square, the big square, the square red and blue things are the quasar itself. And as you can see, it's pretty dramatic. I mean, some of these things are just wild. So anyway, a lot of ATLAS science going on, a lot of ATLAS papers. ATLAS is not like other surveys in that you know, there's a closed set of scientists who have signed up to do the science, and with their sharp elbows, they've picked a certain piece of science that's theirs and only theirs. As far as ATLAS is concerned, all our data should be free, and we're funded to find asteroids, and we're fully funded to find asteroids. So we don't need to worry about scaring up money to do all this other stuff. It just falls out for free. But we're not funded to serve the data. And so we've got kind of a three-tier system here. There's the people who are personally contributing a lot of work to ATLAS, and they're called ATLAS scientists. In return for their work, what we do is essentially give them a free login into our computers, and they can do anything they want. So extract any data they want, do any project they want, and so forth and so on. So Nick Erasmus, for example, is our South African ATLAS scientist. The second tier are people who are at institutions who have contributed to ATLAS. So Sutherland, for example, and SAAO has provided some funding for the concrete, the site, and putting up the dome. And so that's a big deal for us. That would be just really difficult for us to do without the help from South Africa. And in return, those people are not given a login credential, but they can go to Nick and they can, or anybody, any of us, and say, hey, can you give us such and so? So, and we're happy to fulfill these requests. There's no limit, and there's no on the data you can request. There's no restrictions on conflicts. We have a wiki where people are supposed to say what projects they're working on, so that we can manage conflicts or multiple people working on the same thing. And so far, it's been pretty good. But we really want this this tier of people who are at contributing institutions to get really excited about the science, because there is just far, far, far too much science for, you know, for us to do. It's just, it's over the top. And then the third tier is the world. And in principle, the data are free and open to the world, except we can't serve it. It's too much, and we're not funded to do it. And so in practice, what that means is somebody in the world who wants to do something with ATLAS data has to approach somebody, an ATLAS scientist, or collaborate with somebody at an ATLAS institution and get access that way. And at the end of this talk, I'd like to give you some real examples of, you know, let's try doing this. So opportunities. There are lots and lots and lots of things that we can do with ATLAS. One thing that's kind of amazing to me is the low surface brightness universe. So, for example, this picture here on the upper right shows NGC 474, which is an elliptical galaxy with a bunch of rings from infalling stuff. And it's totally obvious. You know, there's this project called Dragonfly that is touting how wonderful they're going to be about finding low surface brightness stuff and so forth. ATLAS just crushes them. This picture that you see here is an average of about 16 images. It's just a chunk that we pulled out of our wallpaper that we use for image subtraction. We have 100 times more data than that that could be stacked if you wanted. So you could improve the signal and noise of this thing 10 to 1 by using all 1,600 images that we've collected so far. And what I thought was really amazing was Armin Rest was interested in looking for light echoes of historical supernovae. So here's a couple light echoes from Tycho, and as you can see, there's this set of scars where bright stars didn't subtract perfectly, and you can see this kind of black-white stuff. The white stuff is the light echo. This is the light bouncing off of dust clouds as it moves along through space. And the black stuff, this is a difference image, remember. The black stuff is where the light was at the moment of that the wallpaper was taken prior to the current observation. So this is MJD 58400. This is what it looks like 150 days later. And it's amazing to me. Look at that, it's moving. And not only that, different little knots of interstellar gas are lighting up. You know, you can go very deep with these. This is a 50-day stack. And you can go very deep and you can actually see things changing. And the transient sky is not just point sources. There's lots and lots and lots of things going on. Gravitational lensing. This, I think, is potentially really interesting. There's micro lensing from star-star interactions. And because we're all sky, you know, it's not like Ogle or something like that, where we're looking at the galactic bulge and the LMC. We're looking at all sky. And so rare events that probe the galactic halo in funny directions are definitely in the ATLAS data. And nobody's looked. We got a trillion detections. And what we do very, very deliberately is when we look at our difference images, we first look for moving objects. Then we look for things that are not moving, stationary transients. If the stationary transients align with a star, we throw them out because we're interested in extragalactic supernovae and so forth. And that's it. So, you know, all the micro lensing events in ATLAS data are just ignored at this point. It's an obvious thing for somebody to take on. And then lastly, these fisheye images that we have, you know, potentially, who knows? You know, are there 8th magnitude flashes in the sky? Are there 4th magnitude flashes in the sky? They definitely occur in the atmosphere, but we've got two fisheye cameras in Hawaii, separated by about 100 kilometers, and they're taking simultaneous exposures, so it's easy to distinguish something in the atmosphere from something that's extraterrestrial. And I think there's some really interesting stuff here. So this is what a fisheye image looks like. Sorry, this is what a number of fisheye images look like that are stacked up. This is what M31 looks like in a fisheye image. And I think there's some real opportunity for discovery here. But anyway, nobody's looked. Anyway, that's kind of a rundown of where ATLAS is at. I think I mentioned that the dome is on its way for Sutherland. The telescope and the mount are done. The cryostat is done. We're still waiting for a CCD. We're still waiting for a Schmidt corrector. We expect to, well, I don't know. We strongly hope to see the Sutherland ATLAS unit operating by the end of 2020, COVID permitting. So what I'd like to do now is actually pause a little bit, ask for any questions, but then I'd like to switch over the screen share to just a terminal window and show you some examples of what it's like to mess around with ATLAS data. You know, what you can do and what it takes to do it. So these are some of the demos that I'll be showing you. But we can, you know, give me an RA and a deck. I've got a piece of paper and a pen here, and we can do stuff in real time. So anyway, questions?
Hi, I have a question. Thank you very much for the talk, John. I'm an astronomer at SAAO, and you know, there's obviously, this is a fantastic data set. There's a ton of, I'm not into asteroids, but I'm interested in variable stars and transients. And I've been giving Nick a hard time over this. So I hope you might be able to say a bit more on how somebody like me can access the data. So in a lot of cases, you don't really know what you're looking for yet. You know, I'm new to this survey. And it's, I mean, I'm sure you can understand that it's a real pain for me. And on anything more than sort of the immediate term, it's just impractical for me to have to ask Nick for everything. So the fact that, you know, we have to go by Nick is a huge limit on what we are able to do with ATLAS. So, you know, I understand that this is a difficult and expensive thing to do, but Assassin, which is of course much brighter, should be a lot less useful than ATLAS to me, but it's not. It's great because I can do whatever I want without having to ask anybody. So there was some talk of this situation improving, and I wonder if you may be able to say anything about that.
Yeah, I mean, what we need to know is what it is you want. So what we've done is we have a real database of what we think are extragalactic transients. Remember, I told you we look for extragalactic transients by looking at all the stationary transients and throwing out stars. And that's for us, that's a manageable database because it has, I don't know, let's say 10 billion detections of, I don't know, let's say 1 million sources or something like that. If we were to try to make a database of all our trillion detections of 1 billion stars, we don't have funding to do that. And it kind of gets over the top. It's possible to do it on a occasional basis. But you know, to do this in sort of real time is, you know, we don't have the motivation, first of all, because until now we haven't really acquired people in the ATLAS community who are interested in variable stars. We didn't have the computers to do it because all our computers are basically purchased by NASA for NASA purposes. But now we've purchased a we've got two computers. One is here and one's coming soon that can be used for other things. And what we need to know is, what do you want? So specifically, if there's a star that you know about and you want a light curve, I mean, we can do it right now. Give me an RA and a deck and we can do it right now. If you more likely want to be able to search all stars for, you know, certain properties or something like that, then I think that's something that we should do. And so I think the right way to do it is to try to describe to Nick, or bring up with Nick, what it is you're looking for specifically. I mean, you know, let's have a real example, and then we can start bringing it about. So what are you interested in?
So I can give you an RA and a deck for an object that I recently became interested in right now, and you can show me the light curve. So that's an example, right? You have this object that you're interested in because whatever, it's a radio source, it has funny properties. But then of course also you can imagine doing a search like put in some blue cut and some amplitude or variability cut and just give me every star in the sky that satisfies that sort of criterion. I mean, it's a little bit, having never looked at the ATLAS data, it's a little bit hard to know exactly what use it might be to one. But there's, I mean, it's clear that there's a huge potential to this data. It would be incredibly useful for the entire community, I think, if it was just a little bit easier to get your hands on.
Yeah, well, so David Buckley, in this demos number 2 that you can see, gave me 3 RAs and decks and said, give me the light curve. And so this is some assassin debris disk or something like that. And this is what it looked like as a function of time. It constant, constant, constant in red O filter, constant, constant, constant in cyan. And then all of a sudden, whoa, whoa, whoa. So that was a specific RA and deck that he knew about because it had been flagged by Assassin, where it's easy to produce the ATLAS light curve. This is what you execute: force.sh, RA and deck, run 50 cores, and red equals 1, meaning don't give me the difference image, give me the reduced image. And then he said, okay, how about AR SCO? That's a fun one. So he gave me the RA and deck, and this is what the light curve looks like. It's a total mess, but of course, if you phase it up with a 3.5-hour orbit, it'll look really interesting. And probably there's, you know, some funny stuff that comes in there from the interaction of the system. So this Assassin thing was bright, 13th magnitude. AR SCO is a little bit fainter, 15, 16. And then he gave me this Swift something or other and RA and deck, and this is what we see. So it's probably got something in there. We're getting down to the limits of what ATLAS can see. Instead of showing this as a function of as magnitudes, I'm showing it as microjanskis here, because this is the difference image. And the things that I notice are, first of all, it's kind of noisier than otherwise I would expect. So here's something that is some magnetic CV or other that somebody or other flagged from X-ray data. And we typically see an RMS of about 18 microjanskis in the difference images. And this thing here is more like 30 microjanskis. So there's probably some small scale variability going on. Also, there's this black line with, if you look carefully, it's sloping slightly. So it's getting slightly brighter over the course of 3 years or whatever it is, 4 years. And so what I would recommend is, first of all, pick some examples, and it's trivial to dump out these things. I mean, this is literally what you type. And if you literally told me an RA and a deck right now, we can do it right now in real time, sharing a terminal screen instead of a PowerPoint screen. And get a sense of what the ATLAS data can do for you. Excuse me. And then try to formulate what a large-scale search might look like. Because we have photometry of all the stars, but it's not in a database. It's all organized according to the observations. And every now and then we take all the observations and we comb it out by RA index, by area on the sky, and we group them according to each star. And then we have a light curve for each star. Does that make sense?
Yes, it does. I will give you a few examples. I'm just and we can do this as a little test. If David Buckley had given you 30 stars rather than 3 stars to look up, would that be sort of the point where it becomes a pain for you?
Oh, no,
300,
no.
would that be a pain?
No.
Actually, Retta, we did that last year with some sources of Mokina Motsoledi for her PhD. So she has light curves of about 30 odd objects of her sample.
Right.
Yeah, see, I need to stress right here, this is what you type. And so for somebody to set up a script that does that 30 times or 300 times or whatever is totally trivial. What we're doing here is we're not actually looking up the existing photometry. It turns out it's a little bit quicker to actually go to the images themselves and do the forced photometry all over again for a specific object. And it's mostly limited just by sort of disk access. It takes about 2 minutes or something like that to do one of these things. And so you could do 30 stars in an hour, and you know, it's easy. The only thing I insist on is no sexagesimal. Coordinates should be in degrees. If we work hard, we can stomp out sexagesimal in our lifetimes. And so give me.
It'll never happen.
Give me a table of decimal RA's index, and it's easy to do.
Sure, I will give that a try then by Nick, I suppose.
Before you
Okay,
go for
me,
the demo, I think someone was raising a hand here. Vanessa, do you want to ask something? Then
hi, no, hi, John. Thank you for the talk. Actually, I think my question has already been answered because it was actually about how the structure of the database or the data are, and I was wondering if you could search by properties of certain objects, but I think that's not yet possible, right?
Yeah, it's sort of possible. As I described, we photometer all the stars. So we have about 1 trillion photometric points. They're organized right now as flat files associated with each observation. And so obviously that's no good for building a light curve at a particular location. What we can do, and it's easy to do, is basically take each one of these flat files and organize them into patches that are on the sky, you know, small regions of RA and DEC, and then associate all those detections efficiently with known stars, and then you've got you know, 1 billion light curves, and you just go through them and you say, are you variable? What's your color, et cetera, et cetera, et cetera. It's also, of course, it sounds kind of stupid to be saying this, because obviously the thing that you'd sort of like to do is just throw all the detections into a database and you know, index on coordinates and just group them using database stuff and so forth. And the problem is that we're just in this uncomfortable regime where with 1 trillion detections and 1 billion objects, databases are just nasty. They're not efficient. And so there are a lot of ways to deal with this. We can obviously you know, shard the sky and make lots of different tables that are comfortably sized. and so forth and so on and so forth and so on. There's absolutely no reason why we can't, on a nightly basis, take all the observations and throw them into a database, or even if we're doing it as flat files, do it as flat files. But our challenge to date has been two things. Number one, we haven't had computers that aren't essentially NASA property. So we were a little bit reluctant to spend a lot of resources to do this. But mostly, we don't have scientists who have been asking for this. And so if you guys want to get involved, man, that's awesome. And I personally am really happy to do a lot of this work because it's so easy to do. It's just, you know, I need motivation and need prioritization. But what I really need is some specifics, like why don't you just do a DR2? You know, as of September 1, 2020, just take all the detections you've got and comb them out and go right ahead and make those, you know, 500 million light curves and run some sort of variability detection stuff on it, as well as kind of mean properties, and make that available, make those mean results available in a database so that they can be comfortably searched. You just have to ask is really the situation here.
Okay, thanks.
Okay, thanks. There is another, Lerodoti.
Hi, thanks for the talk, nice talk. So just two questions. One on the low surface brightness stuff, such as you pointed out for the galaxies.
Yep.
And I guess technically I didn't get my head around it in the sense of, I mean, the difference between the stacking of the difference images versus the stacking of just the actual images. What the stacking of these, what differences are being stacked to get those light, to, you know, those low surface brightness features? I didn't get that. And then the second question is about the cameras, which I guess are targeting faint sources. And I'm just curious, actually, like, I mean, so these cameras are also taking 4 images a night, and are the, I didn't get a sense, because you didn't really say much about these cameras, what kind of resources are being spent on them? Are all their images also being stored? And also like the niche science that you are actually expecting from them, since this is like way outside the NASA project that you are talking about, or their aims. So yeah, I was just curious about what those cameras are really there doing.
Okay, so the cameras are there. Actually, there are bright asteroids, and you know, Ceres, for example, and so we can use them for the NASA program. But it's just one of these things. You know, the fisheye is there primarily to provide us a good view of the sky so that we can safely run the observatory robotically. And we have to be quantitative about it. We can't just sort of depend that there's going to be a human looking at this thing to say, oh yeah, I think I see some clouds coming in. It's got to be analyzed so that it can be used robotically. So there's a really good reason to have the fisheye. The auxiliary camera, I mean, I swear, I would feel so stupid if, you know, the next galactic supernova goes off and it's completely saturated in our main camera. You know, it's one of these things. It's so cheap and easy to do that NASA gives us a certain latitude to do the things the way we think they should be done. And I think this is one of the things that we should be doing. So we're doing it. Anyway, that's the answer for the 35mm cameras. The stacking, it's easy to basically put the images on a common coordinate system and stack them. We do that for the main, you know, for the undifferenced images to the extent of making a static sky reference image, all sky static sky reference image for doing the differencing. And we typically use about 16 odd observations to do that. And we don't need to use more because at that point, the variance in the wallpaper is way, way less than the variance in an image. So it's not going to change the signal noise to stack more of them. So what you're seeing here is NGC 474 with just out of the wallpaper. And, you know, any place in the sky, we have this wallpaper and it goes this deep. But in fact, this is only 16 and there's 1,600 of them. And if somebody cared, there's no reason why we couldn't stack essentially all the image data to make a super duper deep image of the sky. Certainly could do that, but there's been no motivation. As for the difference stacks, this is a case where we think that there's some value to looking for transients that are slow and faint. And so therefore, by stacking the difference images, we go deeper at the expense of losing time resolution. And so we obviously have the individual differences for each image, but we stack the nightly stacks, 4 of them, and then we take those and we stack 50 nights worth, you know, just to make a deep image. And as you can see in this case of Tycho, there's the movement is sort of consistent with not being blurred too much over 50 days. So that's a good interval for this thing. If we stack 300 days, it would all become blurred out because it's moving faster than that. But you know, once again, this is a case where one of the ATLAS scientists said, "Hey, wouldn't it be cool?" And so we decided we'd do it. And now that you guys are